Welcome to my podcast. Today's episode, From Data Silos to Smart Answers, Building a Local RAG Pipeline with Ollama and pgvector. For years, building intelligent applications meant relying on cloud-based large language models, or LLMs, through APIs. While convenient, this approach often came with drawbacks like cost, latency, data privacy concerns, and vendor lock-in. However, the landscape is shifting. Tools like Ollama are democratizing access to LLMs, allowing you to run powerful models directly on your own hardware. This, combined with the increasing efficiency of vector databases like pgvector, is fueling a revolution in retrieval-augmented generation, often called RAG. RAG is a technique that enhances LLMs by grounding them in your specific data. Instead of relying solely on the model's pre-trained knowledge, RAG retrieves relevant information from a knowledge base and provides it as context to the LLM. This enables more accurate, relevant, and trustworthy responses. Many organizations are finding that RAG significantly improves the performance of LLM-powered applications, especially in specialized domains. The promise of running the entire RAG pipeline locally, from embedding to inference, is particularly appealing. It offers unparalleled control, privacy, and cost savings. This is a departure from traditional approaches and aligns with a growing trend towards data sovereignty. This shift is reshaping how organizations build and deploy AI-powered features. The first step in building a local RAG pipeline is preparing your data. This involves breaking down your documents into smaller chunks and converting them into numerical representations called embeddings. Embeddings capture the semantic meaning of text, allowing you to compare and retrieve similar content based on meaning, rather than just keywords. Ollama simplifies this process. It provides access to a variety of pre-trained embedding models. For example, you can pull the Mistral 7B Instruct version 0.1 model and use its embedding capabilities. You'll need to install Ollama from their official site, following the instructions for your operating system. Once Ollama is installed, you can use its API to generate embeddings. The exact command will vary depending on the model you choose, but the output will be a vector, a list of floating point numbers, representing the semantic meaning of your text. These vectors are the key to efficient semantic search. Now that you have your embeddings, you need a place to store them. pgvector is a Postgres extension that adds support for storing and querying high-dimensional vectors. It's a natural fit for RAG applications because it allows you to perform similarity searches directly within your existing Postgres database. First, install the pgvector extension in your Postgres database. Next, create a table to store your embeddings. You'll then insert your data, generating an embedding for each document chunk and storing it in the embedding column. This process can be automated with a script or application. Once your data is loaded, you can perform similarity searches using the similarity function. This query retrieves the most similar documents to your query, based on the cosine similarity between the query embedding and the embedding stored in the database. This is where the magic happens, turning natural language into a measurable distance in vector space. Choosing the right database is crucial for performance. With your data embedded and stored, and your LLM running locally with Ollama, you can now orchestrate the entire RAG pipeline. The basic flow is as follows. Your application receives a user's question. Then, Ollama generates an embedding for that query. This embedding is used to query your Postgres database using pgvector, finding the most similar documents. The content of those top documents is retrieved and combined with the user's query, then fed to your local LLM running with Ollama. Finally, the LLM generates a response based on the provided context. This can be implemented using a variety of frameworks, including LangChain or a simple Python script. The key is to seamlessly integrate the different components. For example, you could use FastAPI to create a simple API endpoint that accepts a query and returns the LLM's response. Utilizing asynchronous patterns within FastAPI can maximize throughput and responsiveness. While a local RAG pipeline offers significant advantages, it's not without its challenges. Scaling can be complex, and running LLMs locally requires substantial hardware resources. As your data grows, you may need to consider techniques like data sharding or distributed embeddings. Furthermore, the choice of embedding model and LLM significantly impacts performance. Experimenting with different models is crucial to find the optimal configuration for your specific use case. Finally, remember to monitor and evaluate your pipeline's performance. Track metrics like query latency, response accuracy, and resource utilization to identify areas for improvement. As you refine your pipeline, consider incorporating techniques like query rewriting and re-ranking to further enhance the quality of your results. To get started, install Ollama and pgvector. Then, experiment with embedding a small sample of your data and querying it using vector. Explore different embedding models and LLMs to see how they impact performance. Don't be afraid to iterate and refine your pipeline based on your specific needs. Remember to consult the documentation for Ollama and pgvector for detailed instructions and advanced features. Building a local RAG pipeline is a powerful step towards unlocking the full potential of AI, giving you control, privacy, and cost savings along the way. Embrace local LLMs. Ollama makes running powerful LLMs locally accessible and affordable. Pgvector is a valuable tool to efficiently store and query vector embeddings in pgvector. RAG is a game changer. Augmenting LLMs with your data significantly improves accuracy and relevance. Remember to experiment and iterate, as the optimal configuration depends on your specific use case. And start small, beginning with a small dataset and gradually scaling as needed. Thanks for listening to my podcast. Visit gladlabs.io for more episodes, articles, and insights. See you next time.